thanks, Brett. Yeah, so as Brett and Matt have already mentioned, my talk is a continuation from Matt's previous presentation. So more specifically, I want to talk about the hydraulic modeling work that we're doing to study the implications of LIDs in terms of watershed hydraulics. So if you're looking at my initial slide and you switch to slide 2, that's where I'm right now. By the way, the slide numbering is in the bottom right-hand corner of my slides. All right, so the critical component of my work here is to set up a hydraulic model for the Little Stringybark Creek watershed. And so on slide 2, if you look at the right-hand side figure, the yellow shaded area in the figure is the domain of my hydraulic model. And the task is to take the data that the flow data that Matt produces from his hydrologic model and inject it into the hydraulic model. And we do that at several locations in the hydraulic model. And those are marked by green crosses across the figure here. Now the north trip, the central trip, and the south trip are actual physical gauges in the site that allow us to monitor flow as different rain events happen. And there's also another physical gauge on the downstream end of the catchment, so that's an X, orange-colored X labeled gauge. And so that allows us to keep track of or measure any outflows from the catchment. To give you a sense of scale, well, first of all, the flow in the catchment goes from the southwest to the northeast. And to give you a sense of scale, the distance between the central trip and the downstream gauge location is about 2.7 kilometers. So not the biggest catchment, but a fair size. So I also added inside the model some virtual gauges. Those are marked by purple lines. So those virtual gauges help us to keep track of the predictive flows in our model. And I'll be showing you later some outputs. It's very similar to some of the outputs that Matt just showed you right at the end here at Q3, so the most downstream of our virtual gauges. All right, so the hydraulic model that we've set up helps us to assess the current flood hazard in the Little Stringybark Creek watershed. And that's something that Melbourne Water is very interested in. And so we're running this whole range of different scenarios where we're looking at different return period events from the 1 year to the 100 year. As well as different durations from the 10-minute to the 24-hour rainfall duration for all these different return period events. And finally, we can also study how LID technologies affect the stream hydraulics in the site. By the way, I have a little glossary at the bottom of my slide here if you get confused by any of my acronyms. All right, so moving on to slide 3. We have some really high-quality geospatial data available for the Little Stringybark Creek watershed. That helps us to parameterize the hydraulic model. Top left-hand corner, we have a digital terrain model obtained through LiDAR technology. The LiDAR point cloud has an average point spacing of 0.8 meters, and the vertical accuracy of the topographic measurements on the floodplain are better than 20 centimeters. So it's a very fine resolution, high accuracy topographic data set. On the top right-hand corner, I'm showing a land cover / land use data set, and this was derived from classifying an aerial photograph of the site. And this particular data set is very useful to assign different spatial distributed empirical mining Zen values to the hydraulic model to capture the flow resistance from different land cover types in our watershed. And then the bottom right-hand figure shows what the actual model looks like. The numerical model that we use is called BRIZO. It's a two-dimensional shallow water flow model developed by Professor Sanders here at UC Irvine. And as you can see, the model uses a mesh of triangular cells to capture the topography of the site. So the topography itself is stored at the nodes for each cell, triangular cell element, and then a Manning-Zen coefficient is assigned for across each cell in the model too. And you can see how the model allows us to refine cells in areas of the model where we need fine spatial resolution. So in this case, that will be the stream channel, and also in areas on the floodplain where there's topographic change. And because we can refine the models, we have a range of different cell resolutions across our site that go from 0.5 meter resolution inside the channel all the way up to 12 meter or coarser on the floodplain itself, where the topography is very flat. And so reducing the cell resolution on the flat parts of the topography allows us to make the model more computationally efficient. The reason why we need very fine spatial resolution inside the channel is shown in the photographs in the bottom left-hand corner. And that's because the stream itself, the Little Stringyback Creek, is a very small stream. It's about 4 meters wide, about 2 to 3 meters deep. So it's a challenge to characterize it hydraulically in a model. All right, so moving on to the fourth slide. We validated the model to an actual rainfall, or to flow that was measured from an actual rainfall event that occurred in May 2014. And our initial attempt to validate the model didn't go that well. So what we did is we injected flow that was measured at the north trip, the central trip, and the south trip that you can see in the right-hand side figure here into our hydraulic model. And we tried to essentially create a hydrograph that you can see on the left-hand side figure. So the solid black line on the left-hand side figure is the measured flow at the downstream location of our catchment. And the dashed black line was our first attempt in validating the model. And what I'm showing here is the Nash cycle of predictive skill for our model, which for our first attempt was 0.34. So on a scale where 1 is a perfect model and a value of 0 indicates that the accuracy of a model is only as good as the average flow of the observed event. We were pretty low on that scale, and so we were not very happy with modeling results. So we went through a calibration process for our model, and the initial step that we undertook was to try running the model with different Manning's N values. So our initial attempt used the Manning's N value for the stream bed of 0.036, which is sort of what we figured was a reasonable value for a vegetated channel. And so we tried out Manning's N values that were lower, 0.02 all the way up to 0.1. And we found that the model was totally insensitive to changing the Manning's N values for the bed. And we could not improve the predictive skill of our model until we realized that by injecting the flow only at the locations where we were measuring the flow for this event, we were actually estimating or under modeling the runoff into the catchment from any subcatchments downstream of those gauges. And so I had Matt run his hydrologic model for this particular event and compute what the runoff was for all the downstream subcatchments that we then injected into the model at the locations marked lateral 1 all the way up to lateral 3. And then you can see that by injecting this extra flow, we improved dramatically the predictions of our model, and that's now the hydrograph shown in the dotted line, where predictive skill is 0.85. We can see that the arrival time of the flow peak is very similar to the observed flow, and actually we are modeling the peak of the flow with an 87% accuracy too. So bearing in mind that the LiDAR data that we're using for modeling has a more or less a 20%, a 20 centimeter vertical error, and the flows in the system are about 2 meters deep, then 10% of that error comes from the topographic data itself that we're using to model the site. So pretty happy with how the model is performing. All right, so moving on to slide 5, I actually want to show you what some of the outputs look like from our hydraulic model. Now, bearing in mind that we've run a lot of simulations, I'm just going to pick and choose some outputs that are interesting to look at. And on this slide here, what I'm showing is the outputs from the 100-year events. So these are the outputs from Matt's hydrologic model under current conditions of LIDs. So this slide gives us an indication of what the current flood hazard is in the Little Stringyback Creek watershed. And what I've done is I've zoomed in onto a 1 kilometer reach of the site. And in this particular reach, the flow goes from top to bottom in those figures. And what we're doing to create these visualizations is we aggregates predicted values from our model across different storm durations for a particular return period event. And then we visualize only the maximum values for each output from the model. So on the left-hand side, I'm plotting the flow depths for the 100-year event. So you can see that a lot of the deeper flows, obviously inside the channel, where the flows get up to 1 to 3 meters deep. Outside of the channel, flows tend to be pretty shallow. There are actually a few buildings just downstream of the south trib, about 5 to 6 buildings that are actually within the flood zone, and experiencing flood depths of less than 25 centimeters, so not terrible flooding. The figure to the right of the flow depth figure shows flow intensities. So this is the predominantly green figure here. So that shows the force of flow occurring from the 100-year flood event. The green shaded areas characterize areas where the flow force is potentially dangerous to children. And in the channel itself, where some of the higher forces are recorded, we can see that the flow has the potential to move cars, and in some locations even to generate building damage if there was a structure inside the stream. Further to the right, I'm plotting the duration of flooding. So again, this is interesting for the 5 of 6 homes that are actually within the flood zone. The graph is showing us that flooding at that location could potentially be lasting 2 to 8 hours. So again, useful in terms of characterizing flood hazard in the site. And then finally, we can tease out what the critical durations are that end up resulting into the maximum values for each output parameter. So in this case, I'm plotting the critical durations of maximum flow depth. And so the yellow shaded area in my rightmost figure shows that the maximum flood depths within that area are actually caused by the 12-hour 100-year event, whereas the area shaded in green, the maximum flow depths are caused by the 24-hour 100-year event. All right, so moving on to slide 6, and still visualizing current flood hazard conditions, I can actually plot what the flow depth and flow extents look like for different return periods. And so on the left-hand side, I'm plotting the return period for the 1-year event. So we see a very small flood zone, flows very shallow outside of the channel itself and only deeper inside the channel. And there are actually no buildings within the flood zone. Moving on to the 10-year event, so the figure right in the middle, we can see that the flood zone now has expanded quite a bit. We have several buildings within the flood zone, but flows are still pretty shallow. And then as we move to the 100-year event, we can see that the flood zone is actually very similar to the 10-year return period event, but the flows are starting to become deeper inside that flood zone. All right, so how do LIDs impact the stream flow in our Stringybark Creek catchment? And this is a plot that's somewhat similar to the plot that Matt showed earlier. So here I'm plotting for the downstream end of the catchment, the cumulative discharge for 4 different events with different return periods. So the 1-year return period, the 10-year return period, the 50-year return period, and the 100-year return period events. And the blue line shows the current LID conditions within the catchment, whereas the red line shows the conditions, the cumulative discharge, during a full implementation of LID systems in the catchment. And you can see that as the return periods increase and the durations increase, the LID systems become less effective at retaining the runoff from the longer duration rainfall events, and they become less effective at mitigating flood hazard. So what does this look like if we plot the data spatially? So and I'm on slide 8. On the left-hand side, the two figures again are showing flood depth and extent for the 1-year return period event. And I'm plotting, I'm plotting the flood extents by return period under current conditions and under full LID implementation conditions. And you'll see that the two figures actually look very, very similar. And the reason is that when I plot extent and depth by return period, because it's a data set that has been aggregated by all the different different durations of the rainfall events, the events that end up generating or contributing the most to the flow depth are the longer duration ones, which are the ones that are less mitigated by the LIDs. And so the two figures on the right show the critical durations for maximum flood depth for the 1-year event under current and LID conditions on full LID implementations. And you can see that the areas marked in red are which are predominant across this flood reach are the ones that contribute the most to flow depth, and it's a 24-hour event, which is the one, again, less mitigated by LIDs. So to actually spatially visualize the impact of the LIDs on flooding, and I'm moving on to the slide number 9 now, I actually have to plot the flow depths and extents by duration. So on the left-hand side, I'm plotting the 30-minute, 20-year return period event under current LID conditions. So you'll see a little bit of flooding occurring there, sort of in the center of the figure. And then on the right-hand side, I'm plotting the 30-minute, 20-year event under a full LID implementation condition. And you see that because it's a shorter duration event, the rain tanks are very efficient at capturing the runoff from the storm, and you'll see no out of bank flow at all. All right, so to summarize my slides here, the current flood hazard conditions in the Little Stringyback Creek watershed are minimal. There's only very few buildings impacted, but we do see quite a bit of flooding along the lower portions, the lower topography portions of the floodplain, and so we need to protect those from development in the future in case further development will occur in the watershed. LID technologies that we've tested, rain tanks and infiltration systems, seem to be effective for short duration events. But as these events have larger return periods and longer durations, then the rainfall saturates the LID systems very quickly, and they become less effective at mitigating flooding. And so if we're in a site where we need to mitigate flooding further, that we also have to look at complementary LED technologies to be able to capture any other runoff. And so we could look at potentially retention basins, urban retention basins, to capture some of that runoff in a safe way. All right, that's all I've got.
Great, thank you, Joe. So did anyone have any questions? I know that we're running a little over schedule, but we did still have the round table. I guess we could kind of just go straight into that if everyone's schedule is permitting.
Thank you, Joe. I thought that was a great talk. I did actually want to ask one question, and that is one of the potential benefits of LID, especially if there's an infiltration component, is increasing base flow in streams. I'm just wondering if you can comment on the possible long-term interactions between sort of that endpoint and flood risk, presumably with higher base flow, then the flood risk calculations change as well.
Yeah, base flow. We are modeling base flow. We're adding base flow to our models. With the hydrologic model that Tim's built, he actually injects base flow or computes base flow before the rainfall event hits, and we do model that in our site. But I don't think we've really looked at how that can change over time. I mean, the events that we model are still pretty short duration, so I don't think. I think what we assumed was that there was very little flow prior to a rain event occurring. So what we could look at is, what happens if maybe several storms hit at the same time, and the flows in the stream are actually increased when the second storm event hits.
Yes, Dan. Didn't I have a student, Jeremy Bonner, who is exactly looking at the question about the fate of infiltrated water from stormwater contaminants. So, hopefully, by the time Jeremy finishes, we'll have a bit more insight about what considers infiltrated water. So.
Matt, I don't know if we can hear you.
Can you hear me?
Yeah, Matt, I'm sorry, I didn't hear you. But Tim, did you have anything you might want to add, or can you channel Matt's comment?
Yeah. So Matt was just making the point that we are specifically trying to understand the fate of base flow, and particularly infiltrated water from things such as infiltration systems. In particular, we have some kind of questions about whether infiltrated water really takes the classic groundwater path, or whether it finds its way into the stormwater network or other preferential flow paths. So there was some work done by Korschel and Belt in the US that talked about this concept of the urban karst, that you've got this dense network of underground trenches that convey infiltrated water. And so the implications of all of these LIDs on base flow is probably much more complex than the theoretical model. And Matt and I are supervising Jochen, who's trying to investigate this. So yeah, another stay tuned.
Yeah, just a perspective from Orange County. I know that for the places where there is shallow groundwater, there are drains. We call it French drain, where they can actually lead the potentially locked water away from the foundation. So it's just mostly for the structural integrity of buildings.
Mm-hmm.
I do have a question about the approach. I think for LID, from the practical point in Orange County, the requirement now here is actually try to not to remove the impact from storm, but to actually 2 points actually. One is to we try to just restore the pre-development hydrology. I don't know if that's something you wanna you did model. The second one is actually even for the LID, we try to deal with the impact from a certain storm event. I think you actually showed that. We just practically it's not possible to deal with large storm events.
Yeah, I mean, that seems to be in line with what the model is showing, that once you get to the large events, you probably will have to deal with some level of flooding. In terms of the hydrology, Matt, do you have any comments about the pre-hydrologic conditions?
Yeah, so the sort of systems that we've modelled are designed in a way to replicate the pre-development hydrology. So of course there's uncertainties there about the fate of infiltrated water and is that restoring the low flows. But these systems are designed in a way to mimic as close as possible the pre-development hydrology. So you're not going to replicate it 100%, but a lot of our work is showing both modelling these systems at small scales and actually monitoring them at small scales that they, if designed appropriately, they can work in a way that is very close to the pre-development hydrology.
I had a quick question from my side. This is Stan again. It's super impressive what you guys did, both on the hydrology and the hydraulics work. But I'm wondering, to what extent is this something that can be eventually routinely implemented, or is it going to remain the domain of a research exercise, given the enormous amount of data that has to be acquired to run the models, for example, LiDAR data and so forth?
Mm.
Yeah, it's not just the data, but it's the modeling itself is very time intensive. So yeah, I mean, I guess as the computers become faster and as our models become more efficient, there might be maybe down the line some ways to streamline some of the hydraulic modeling. I guess in terms of hydrology, the monitoring is definitely crucial. But I think the research project that we're currently working on right now is really just to inform how useful these SCMs can be and what the limitations are in terms of flood risk. So we don't necessarily need to replicate a full-on, replicate the same scale of modeling approach that we're doing right now. We could figure out, where the breakpoints of the system right now, and maybe focus the modeling to more specific events that can be used as indicators of how well a system is performing.
And yeah, just further to Joe's point, I think this is a really important proof of concept that it might motivate, say, practitioners, if they've got a catchment that flooding's a problem, that they might actually consider SCMs as a genuine alternative for flood management. So,
while knowing the limitations, of course.
Yeah.
Okay.
Yeah, I think that's a really crucial point, right? Because you're going to have to change the way flood control districts think about managing urban flood risk. And so if you can make the case that this helps rather than hurts, I would assume that sell would be easier.
Yeah.
Yeah, and look, it's an interesting philosophical discussion, because as a few people have now shown, perhaps the benefits of these technologies kind of reside in the, let's say 30-year and under storms, but they also provide a whole lot of other benefits to the community. And so then the question is, as a government, how do you want to spend your money if you can reduce flood impacts so that there aren't impacts in the sort of up to 30-year kind of events, and you deliver a whole lot of other benefits to the community? Is that a better investment than dealing, with up to 50-year or up to 100-year, but delivering no other benefits? And I'm not saying I know the answer to that, but I think it's a question worth, discussing in an open-minded way.
Mm-hmm. I agree, and when we look at these plots of sort of benefits versus return period, sometimes we also forget that these frequent events are just that. They happen all the time compared to these extreme events. And so the benefits you see at the higher frequency site are going to be seen over and over again compared to these really infrequent events, which is another thing.
And I know that one of the common approaches to getting at this is to calculate AAD, annual average damage, or annual average cost, however we want to call it. And I think when you do that sort of analysis, you start to see, the return on investment for these higher frequency, lower magnitude events, don't you?
Mm-hmm.
I have a question. This is Meg. Do these analyses assume that the performance of these systems is stable over time, so that you're not going to have an infiltration trench that becomes clogged or some such?
Yeah. So great question. So yeah, we're assuming perfect operation, which we know in reality. For example, a lot of the rainwater tanks that we've monitored over the last couple of years, probably 20 to 30% are not working as they should. So I think a further potential improvement of work could be to model some systems that aren't performing as they should, or just not modeling them, modeling only 80% or something like that. So, yep.
Yeah, so down the road we could look at a sensitivity analysis of what happens if some of these systems are not working to full capacity, and what the impacts would be in the community if we do find that a certain percentage of the systems are underperforming. But in terms of figuring out what the probability is of these systems not performing well, it's just very difficult to calculate that. So at this point we assume that the systems are working, but I mean that's a good point. Maybe somewhere down the line we should model what happens if they do not.
Tim, something else that was on my mind. You've had experience now working in the community and trying to get people in the community to participate in adopting stormwater control measures at the household level with infiltration trenches and with rain barrels and so on. And so, the flip side of the flood risk, issue with the extreme events is the possibility of reducing vulnerability, and as opposed to focusing on minimizing exposure. And I'm just wondering if there's, I guess a parallel level of community participation that could surround the idea of sort of accepting some level of vulnerability or exposure to flooding, and thinking about designing differently or adapting structures that are within a vulnerable area, so that maybe we could tolerate some level of increased inundation of the floodplain. And so I don't know if you guys have had any of those discussions with Melbourne Water or anybody else, doing both sides of it, just on the one hand managing source control, but on the other hand managing vulnerability.
Yeah, that's a great discussion, right? So the answer is no, we haven't directly, and in part it's because of the reality that this catchment is not at all one of Melbourne Water's priority catchments for flood management. Our reason for tackling it is because we've got such great data about it and we're doing such significant things to it. We wanted to explore those. Having said that, Melbourne Water has been talking to us about that question more broadly, and they've been exploring this independently more broadly. How do their new flood management plan, in fact, asks exactly this question: are there other things we could do in terms of making the community more, let's say, resilient to flooding?
Mm-hmm.
But we haven't yet tried to take some of the ideas of Little Stringybark Creek and then apply those in a flooding way. And I hadn't thought about it, but actually, as soon as you were speaking, I was thinking, yeah, it would make a whole lot of sense. And in some ways, it might almost be an easier engagement than we had, because a lot of people, they don't even know where the nearest creek is. They live in the catchment, but they don't know it exists. So to get them motivated takes building an awareness, whereas for flooding, generally they'll tend to be aware. Sure, they might have forgotten, or they might have just moved into the catchment, might not know, but most will. So I think it really would have good potential. We haven't explored it, and it's something we can discuss.
Yeah. Well, also maybe I think I know the answer already, but if John wanted to weigh in on whether within the U.S. there's any thinking that we could go to a community and say, talk about sort of adapting to tolerate some level of flooding, to sort of become more resilient to flooding, as opposed to just the attitude that the goal of our civil infrastructure should be to prevent flooding altogether. I mean, are we having those conversations in the county, or is that just not really a reality of what we're seeing?
No, I don't think it has been brought up so far, and I think people think about flood risk and water quality. They think they're even though they are related, but they have a different priority. For the flood control folks, it's a absolute priority for them to put the safety and protection of the the public health, public safety at the very highest level. Water quality, not to say that it's not important, but in terms of the priority in the face of the flooding, I think it's secondary.
Mm-hmm.
So at some point, I do think that when we talk about flood risk abatement, there is always for example LIDs. There's always a water quality benefit to it, but when when we compare these two issues, I think almost always flood protection is a higher priority.
Mm-hmm.
Yeah.
Great, thanks.
So John, this is Stan. Just to follow up on that, do you see any trends in the county toward looking more holistically across flood control and water quality protection, ecosystem protection, or are the institutions pretty siloed?
I think it's getting much better, for the flood control folks, because right now when we try to implement water quality improvement projects, as you can see the priority list for the public available land, the flood control channel, the retarding basin, and things like this are still, number one places where we actually implement them. But these are just it's like a fringe benefit for them at this time. I hope that in the future, when we design flood control features or multi-benefit places like Prado Dam, people can think more holistically. I think we're getting there, but I think it's gonna be a process.
And it might behoove us to give some thought about what parts of the system have maybe the most potential for synergies, because I think if we come along and maybe that Santa Ana River shot that I showed, the idea that could be transformed maybe is just going to cause agency people to want to laugh and think we're crazy, right? But there may be scales at which this is more realistic, and maybe there are some smaller concrete line channels here and there, or pipes, and places where we can get more traction. Then and that we could do the region a service by helping to identify what those are based on trade-offs between water quality and ecology and sediment management and flood risk and vulnerability and all those things. But
yeah.
Okay, so on that note, any other comments?
I think I need to take off in a few minutes. I just want to bring up a kind of practical point from what Los Angeles, San Diego, and Orange County are doing. Right now we're doing a watershed management plan. At different places we call it differently. But the fundamental issue is that we're looking at different watershed. Mainly the starting point actually is water quality, because there are a lot of regulations to for us to do things to deal with it. And right now the newest version of this water quality management plans are actually based on directly or indirectly to LID. So what happens was, there are different, resolutions and, different details of watershed models. And, what we did was we put LIDs at the, places where they could be implemented. And then based on the performance in terms of water quality and hydrologic parameters, we can simulate, how the watershed will respond to the implementation of LID, so that the receiving water, hydrology, and water quality can meet the regulatory requirements. So these plans are, for each watershed, I think they could cost, hundreds of millions of dollars, but still, these are the things that all the watersheds are planning on doing. I'm guessing that it probably takes decades to actually achieve the goals we try to achieve, but that's the direction we're going. So, maybe 5-10 years from now, we can actually see a pretty significant change in the implementation of LID, and we should be able to see the response in the receiving water. So this is pretty much on the practical level in Southern California.
Excellent, John. So I suggest that, well, let me say thank you to everyone for participating. Thank you to Stan for inspiring this activity, and for James for making it happen. I learned how to use Google Hangouts for the first time. Some practical learning endpoints there. We'll document those as part of our achievements.
Essentially, it doesn't work well when it's raining outside.
Any other thoughts?
Thank you, everybody, for a great session. I think that we got a lot of great ideas and synergies out on the table. So it'll be a nice resource going forward.